How do you make a 1.2 million square foot conference center that's as welcoming to wildlife as it is to people?
To attempt a green roof on this scale was a huge undertaking, a huge risk.
How do you build a beautiful bridge that can also rise 160 feet in the air?
You can move the bridge with one hand, huh? You know, it's crazy.
And how do you construct a 668-foot tall cocoon-shaped tower in an earthquake zone?
You've got to make sure that your beautifully designed building doesn't essentially rip itself apart.
This is the age of the extraordinary.
It's totally different from anything around it. It's like a visitor from another planet.
Where ingenious engineers have unleashed unchecked creativity. Now, their secrets are revealed as we discover the amazing stories of their construction.
It is simply mind-blowing. I mean, how do you come up with an idea like that?
To try and understand, how did they build that? Next time you're up in Vancouver, I recommend you check out the greenest convention center in Canada. It has a 6-acre living roof with 400,000 plants and a lawn which takes 6 gardeners 2 weeks to mow. Since opening back in 2009, there's been a real buzz around this building. That'll probably be the 250,000 honeybees who call it home. Vancouver, British Columbia sits over a series of islands on the edge of the Pacific. Since the millennium, the city has been restoring this coastline and bringing back its biodiversity. So, how do you build a huge new waterfront convention center that will have a positive impact on this landscape?
We have to feel responsible for what happens on this site is going to impact the whole waterfront.
The answer is this extraordinary eco-friendly structure that straddles the shore and the ocean.
Constructing anything on water is way more difficult than building on land.
Creating wildlife-friendly areas below the waterline and above it.
6 acres of living landscape. Just imagine how much weight that's adding to the roof.
All wrapped up in a spectacular, asymmetrical 1.2 million square foot building.
There isn't really a precedent in Canada for building a structure of this size.
This is Vancouver Convention Center West. So, how did they build it? It's the early 2000s. LMN Architects have been given the job of designing a new convention center for Vancouver, over 3 times the size of its predecessor.
This is one of the biggest projects we've ever designed. We have to push the envelope.
An 11-acre waterfront site is chosen by the city. But the plot isn't big enough for what they need.
We wanted to keep it intimate, but we needed the square footage as well. So we needed to build at least 40% of it over water.
As if that wasn't challenging enough, the city also wants the team to rejuvenate this part of the coast. Known as Cole Harbor, it's a former industrial site which has undergone gradual redevelopment.
This site was the last remaining piece of the downtown waterfront that had not been restored.
The team needs to create an epic new building for the city that will leave this part of the shoreline in a better state than they found it. First, they'll have to find a way to fit a building bigger than the plot onto the waterfront site. This will mean building out into the bay on a specially designed platform which is strong enough to support the building. They'll need to figure out how to squeeze a massive event space and enough parking into the striking structure with its views across the water. But what will make this building really special will be the way it helps the local environment. Under the waterline, they need to design and build a pioneering habitat to encourage local wildlife to return. And the whole center will need to support a green roof the size of 6 American football fields. It's 2003. Design work is underway, and the first curveball comes when Vancouver is chosen to host the 2010 Winter Olympics.
There was a decision that the convention center should serve the Olympics as the press center.
The building will play host to reporters from over 80 countries. It's an honor, but it sets off a 7-year ticking clock.
So that may seem like a long time, but in building development, that's a pretty short order.
Time is of the essence. So before they even finish designing the building, they start constructing a solid base called a marine deck.
The typical foundation for marine decks, like the one used here, includes driving piles into the seabed and topping them with pile caps. These are large concrete blocks that evenly distribute the load, creating a foundation stable enough for construction.
For this building, they will need a 1,000-foot-long deck. That means driving 900 piles 200 feet down until they reach the bedrock. With the Olympics approaching, maintaining the necessary pace requires military efficiency.
The marine deck was built from the east towards the west, and it was in a kind of assembly line type of process where pile driving was started at one end, and then pile caps were started while the pile driving was moving further west.
With the piles in, the concrete deck takes shape on top. It's a huge job, but after 2 years, 20,000 tons of steel and 34,000 cubic yards of concrete, finally, they have a base for a new conference center. The next challenge is to engineer the structure. The architects want big open spaces inside and huge sloping glass windows on the outside, and an enormous green roof on top. Coming up with a structure that's strong enough to achieve all of this is extremely complicated to get right.
You don't really see the complexity of it until you see it in 3D and 3D modeling. Nothing comes together square. Everything's got an angle, a two-directional angle, slopes.
The team opts for a steel frame, which will handle these challenges better than concrete.
Steel is the perfect material for spanning large areas. It's strong, it's durable, it's relatively light compared to concrete, and doesn't need nearly as much maintenance.
But in engineering terms, what is considered light is relative. Some of the pieces of structural steel weigh 730 pounds per foot.
These trusses would be delivered to the project site on very large trucks and then have to be hoisted into place with very large cranes on the marine deck. So the marine deck had to include capacity for these large cranes to be able to literally build the building on top of it.
The next challenge the engineers face is making sure the building will be strong enough.
Vancouver is a high seismic zone with large earthquakes that happen every 300 to 500 years, and the next big earthquake is expected in the next 100 years.
To ensure the conference center is prepared for the threat, the team designs and fits seismic braces. These huge springs act like shock absorbers on a car if the building gets hit.
As it sways one way or another, it's getting a little bit of help out of this spring, increasing or decreasing in load as the building sways one way or another.
It's a great solution that will allow the team to finish the huge frame by June 2007, 2.5 years away from the Olympics. But before that, the team has to work out a way of making the building a safe habitat for an endangered local fish.
One of the really fundamental things that's important in this region is the salmon migration. And the baby salmon will swim along the shore. They want to be in shallow water so that they can avoid predators.
The team has a bold idea. To help stem the rapid decline in the population, they want to create shelter for migrating young salmon and other species in the underwater parts of the building. The daunting task of designing it falls to new project engineer Daniel Leonard.
I had just graduated from university, and they came to me on my first week and said that they had this really challenging aspect of the project that they wanted me to lead.
The problem is, there's no blueprint for a structure like this.
You're basically told, please do something that's never been done before in the shortest amount of time possible and do it on time and on budget.
In Vancouver, the team behind a new waterfront conference center is racing to finish it in time for the 2010 Winter Olympics. First, though, they need to work out how to create an environment around it that will protect the endangered local sockeye salmon. Their solution is to create a series of precast concrete benches that will mimic the natural shoreline, periodically exposed and covered up by the tide, with plenty of hiding places for ocean plants and animals.
The benches were built with ridges and also tidal pools in them to provide the maximum amount of habitat for the surface area that was provided. The materials were chosen to replicate that shoreline as well, exposed aggregate concrete to allow marine growth to attach to the exposed aggregate.
Because these benches will hang off the building and below the high tide line, there's no way that they can cast the concrete in place.
All of the leg units and the plank units were built at a precast concrete factory on Vancouver Island, and then they were barged over, and then a massive 300-ton capacity crane was used to pick up the legs and to swing them in place and to clip them onto the side of the foundation. And all of the legs, all 76 of them, were installed in 4 days.
Scientists will carefully monitor the impact of the structure on the sockeye salmon population. For now, though, with the Olympic deadline fast approaching, the team turns its attention to the roof. The ambition is to transform all 6 acres of it into the largest green roof in Canada.
Vancouver is actually one of the leaders in green roof development. It has a long history. Some of the earliest green roofs are just in this neighborhood here.
Green roofs look beautiful, cool buildings, and attract wildlife. But creating one this large is unprecedented.
To attempt a green roof on this scale was a huge, huge undertaking, a huge risk.
The first problem is making sure the roof isn't too heavy.
6 acres of living landscape. Just imagine how much weight that's adding to the roof.
The engineers calculate that the structure can take up to 6 inches of compacted soil. More than that, and there's a risk it could collapse. Work starts by adding an even layer of gravel topped with soil.
We had truckloads of gravel, truckloads of soil. That was all craned up, and then we had conveyor belts set up to distribute the soil.
To add to the challenge, some sections of the roof slope steeply, so the team needs to add special stabilization mats with pockets to stop everything from sliding downhill. Then they are ready for the mammoth planting job.
6 acres, 400,000 plants, and 40,000 bulbs involved in planting this space.
All of the plants are native to the area in order to make sure they thrive on the exposed roof. And all of them must go in the exact right spot.
There was this kind of grid that had the corresponding colored tags. So let's say, the native strawberries were going to be in the pot with the blue tag, and the asters were going to be in the pot with the yellow tag.
With the Olympics less than a year away, 800 people are needed for the final push to finish the building's crowning glory, the steeply sloping roof.
At times it was tough when we were working up here.
The biggest challenge creating this space was the safety element. It was very cumbersome and uncomfortable to be attached to a lifeline, but it was absolutely necessary to work along the perimeter, which is about 15 feet from the leading edge.
It takes months of backbreaking work to complete the job.
You are continually bending over to plant. You had to move at a decent pace. It was tough, but it was fun.
In 2010, Vancouver Conference Center West is revealed to the world's press.
The opening day of the 2010 Olympics was such an exciting day. We were lucky to welcome people from all over the world.
The 1.2 million square foot center has the largest ballroom in Canada, and the main hall can hold 15,000 people. But it's not just human visitors it appeals to.
The habitat structure has a lot of marine life growing on it, and that marine life actually grew much faster than anybody anticipated within months of construction and has continued on over the past 14 years.
The roof has also flourished and is attracting pollinators. And irrigated by recycled wastewater, it's helped to make the center one of North America's greenest buildings.
The building is currently rated as a double LEED Platinum, and that is the highest standard of sustainability rating you can get as a building like this.
It's an emotional experience to see a building that is occupied by fish and by bees and by birds and by plants and by humans. Working on the Vancouver Convention Center, it was a reminder of how deeply interconnected everything in our world is.
When the beautiful French city of Bordeaux needed a new bridge across the River Garonne, they didn't want some regular, boring bridge, something that just carried vehicles from one side of the river to the other. Where's the fun in that? No, they wanted something different. So different, in fact, that when elevated to allow tall ships to pass below, it doesn't look much like a bridge at all. It looks more like a work of art, which it most definitely is.
This is the magnificent Jacques Chaban-Delmas Bridge.
Watching it open, you feel like you're in like one of the Transformers movies.
A mechanical marvel that can lift 8 lanes of roadway 160 feet.
It's like it was alive, no, this bridge?
Built over one of Southwest France's busiest rivers.
It was totally crazy, no?
It required gravity-defying engineering.
The bridge lifting span by itself weighs around 5 million pounds.
It now stands as Europe's tallest vertical lift bridge. So, how did they build it? It's 2008, and the beautiful historic city of Bordeaux in southwest France is changing. Historically, development was concentrated on the left bank of the River Garonne. But now, new neighborhoods are springing up across the water. As Bordeaux grows, traffic is becoming a bigger and bigger problem. The city is one of the most congested in France, and its transport infrastructure, especially its bridges, are at a breaking point.
On avait un déficit de franchissement de la Garonne pour les automobilistes et pour les piétons et les vélos.
The city needs a new bridge. But the ideal spot to build one is over a part of the river used by cruise ships to access the city's historic port.
The requirements were to design a bridge that could allow tall ships to pass and carry pedestrians and cars and a tram in the future.
They can't just build a high bridge because it needs to connect to the existing roads on the riverbank. So they settle on what's known as a vertical lifting bridge.
A vertical lifting bridge is when the whole central span lifts straight up into the air. The problem is that it usually takes a whole lot of clunky mechanical gear in order to make it possible. So they're like the ugly ducklings of the bridge world.
While a vertical lifting bridge might be what the city needs, an ugly duckling is the last thing it wants.
The town of Bordeaux, it is an 18th century historical town with a harmony and a skyline super beautiful. And the bridge will be in the middle, so the project must be in harmony.
The specialist bridge architects take inspiration from the steeples of Bordeaux's many ancient churches.
It was the adrenaline moment to find the design of the pylons. It was so exciting.
The design combines beauty and practicality, but building it won't be easy. Working on the busy river, they'll need to create foundations in the water and find a way to protect it from being hit by passing ships before constructing 4 elegant 250-foot tall pylons. The massive road deck will have to be brought in sections and carefully positioned. Then they'll need a lifting system that's small enough to be hidden inside the towers, but powerful enough to lift the huge 2,750-ton central section, which will carry 8 lanes of traffic as well as pedestrians and cyclists. It will be a mammoth test for the whole team.
Un projet de cette envergure nécessite des équipes très compétentes et qui ont beaucoup d'expérience. C'est un véritable challenge.
I was a little bit afraid too. It was stress for me.
It's October 2009. Construction begins, and immediately the team is faced with its first challenge: creating underwater concrete foundations that will be strong enough to hold up 4 250-foot tall concrete pylons.
Building the foundations of a bridge over deep water is always challenging.
Because the river's busy here, it's even more complicated. Rather than create the foundations on site, they plan to prefabricate 6 concrete foundation boxes in a dry dock up the river. Then, they'll float them into position and secure them to piles sunk into the riverbed. The 2 largest boxes will become the bridge foundations. The 4 smaller ones are there to protect the structure from potential ship impacts. In 2010, 3 miles from the bridge site, the team starts to work on the boxes. Each will be made using between 3,000 to 6,000 tons of concrete reinforced with steel. And they're working against the clock.
Le temps d'utilisation des formes de Radou est très calé dans le temps. Il fallait que le planning d'exécution soit en parfaite adéquation avec la mise à disposition de la forme de Radou, ce qui n'était pas très simple.
After 5 months, the first foundation boxes are ready. The dry dock is flooded, and then they set out along the Garonne. It's a tense moment for the team.
La Garonne est un fleuve très capricieux entre la haute marée et la basse marée. Il y a des courants qui sont très importants.
To keep the boxes steady, each needs 2 tugs pulling it. Navigating the carefully planned route, avoiding sandbanks and the most dangerous currents takes 4 days and nights, with the team working in shifts. Now, the box can be carefully slotted into place and flooded with water to sink it to the riverbed. Then, the water is replaced with concrete to make it permanent.
Faut le voir pour le croire. Des pièces aussi massives qui pèsent des dizaines de milliers de tonnes puissent comme ça flotter sur la Garonne et venir être posées au centimètre près.
Over the next few weeks, the rest of the boxes follow. And the team begins work on the 4 reinforced concrete pylons. Next, though, is possibly the team's greatest challenge: creating the road that will run between them. The crossing will be made of smaller fixed sections on each side, acting as ramps, and a massive middle section, 380 feet long, that will rise and lower.
So 120 meters long, 30 meters wide, 2,500 tons of steel and in one piece, so it was crazy.
What makes things even trickier is that the only company that can make these massive slabs is based in Venice, Italy.
These sections are so big that they can't be brought by road. They have to be floated to site.
Only this journey is a 3,000-mile trip across the Mediterranean Sea and into the Atlantic Ocean. And it's not easy sailing.
Il y a eu une petite tempête sur l'Atlantique donnée et la barge avec les remorqueurs a été obligée de se mettre à l'abri dans le port de Lisbonne.
But after 3 tense weeks at sea, the decks finally arrive on site, ready to be fitted. That's if the team can find an opening in the river's hectic schedule.
The Garonne is a very busy river. It was not permissible to block the channel for long periods of time.
The team needs to lift this 2,500-ton slab into position as quickly as possible. It's too heavy for a crane, so once again, they turn to the river for help.
On a high tide, the barge will float the spans above their final position. Winches rotate them through 90 degrees to line up with the fixing points, then wait for the tide to fall and lock them back in place. But the tides have to be just right.
In Bordeaux, the team building a vertical lifting bridge over the River Garonne is relying on the tides to help them position the enormous central span. It's a clear morning in the summer of 2012. The tides are set to be perfect, and the city is watching.
A lot of people in Bordeaux was here to see this moment.
The high tide helps to float the 380-foot-long central span into position. It must be inched into place with pinpoint accuracy. As the tide falls again, the central piece locks onto the pylons perfectly.
It was a fantastic moment.
Now, the team faces its final challenge: making sure this huge central span can be lifted effortlessly into the air.
The lifting span by itself weighs around 5 million pounds. In order to raise that, that's an incredible amount of energy.
As if that wasn't tough enough, the lifting system needs to fit into the bridge's elegant, narrow pylons. The secret to this phenomenal deadlift is counterweights.
Counterweights are an engineer's ace card. By balancing the weight of what you're lifting with something almost as heavy moving in opposition to it, you can minimize the lifting force needed.
The team calculates that in each tower, they need a 660-ton counterweight, supported by 4 massive pulley wheels with super reinforced cables.
We were able to create a very, very long, thin counterweight, which is not typical in a vertical lift bridge.
If they've got the balancing act right, they'll only need 4 modest engines to lift the enormous bridge.
Those motors are actually only 150 horsepower due to the balance that we were able to achieve, which greatly reduces the power consumption.
Good for the city's energy bill and good for the planet.
You can move the bridge with one hand, huh? You know, it's crazy.
March 17th, 2013, and the bridge is finally finished. After 10 years of planning, design, and construction, it's time for the people of Bordeaux to test their new bridge.
Pour les gens qui ont la chance de le voir se lever, c'est toujours un moment assez époustouflant de voir cette masse se lever.
The bridge opened flawlessly. The French military sailboat came through the bridge, beautiful image.
The first time I see it go up, I remember that there was no noise, nothing. It's beautiful, yeah.
The bridge, combined with a new tram system, has helped ease traffic in what was one of France's most congested cities. And it continues to perform staggering feats of strength with faultless elegance.
We cannot build anything better than this bridge here.
We did something great together. Wow, we did it.
Think you know what a school looks like? Well, visit Tokyo and think again. Because this stunning tower houses not one, but 3 separate schools and 10,000 students within its super strong cocoon design, as well as a retractable helipad. Helicopters on the run to school? Wow. Oh, and if you're wondering just how strong super strong is, in 2011, the tower was caught in a magnitude 9.1 earthquake. Structural damage? 0.
Introducing Mode Gakuen, or the Cocoon, as it's affectionately known.
This building really just looks beautiful.
One of the tallest colleges in the world, it's as clever as it is stunning.
This building has a retractable roof that helicopters can also land on. Did you have that at your university? Because I didn't.
With a design that was breathtakingly ambitious,
続けていくためにどうしたらどういうふうなことができるのか、それはやっぱりやったこともないことですので。
When I first saw the design, I thought it was a good challenge.
it would take every ounce of ingenuity and effort to finish it.
Making a structure as complex as this is exhausting.
Yet the final result would transform the Tokyo skyline with a skyscraper unlike any other, loved by those who use it.
This building is a very iconic place, and I really love to study here.
So, how did they build it? At the end of the 20th century, Japan was languishing in a recession. But by the mid-2000s, there are signs of a burgeoning recovery. Investment is up, and people are beginning to feel positive about the future. So, the Japan Educational Foundation decides now is the perfect time to expand.
もともとファッションの東京モード学園の校舎だけだったんですけれども、テクノロジーやメディカルの学校も増やすためにコクーンタワーの建設が必要だったんです。
In one of the world's most densely populated countries, finding space to build is tough. The plot they found is less than an acre, and on it, they've got to fit 3 new colleges.
Our lands are not as big as we would like to be.
Space for development in Japan is premium. If you want to build anything new here, you have to be an incredible problem solver.
The man tasked with finding the solution is architect Paul Tange.
Of course, there is a functional requirement, but they wanted to see something that they have never seen before. We finally came up with the idea of Cocoon.
The inspiration for the cocoon design comes from the students that will study here.
We nourish them, cherish them, give them everything we have, knowledge, and eventually they will come to beautiful butterfly and fly off to the world.
Constructing a building that looks like a cocoon will demand ingenious design and creative engineering. First, it's going to be a very big building in an earthquake zone, so its foundations need to be super strong. Then, they will have to work out how to squeeze 10,000 students into one building on a site that isn't big enough. Next, they'll want to construct the curtain wall from huge glass panels, somehow using them to create the natural look of a cocoon. And finally, they'll have to work out how to land an emergency helicopter on a building with a curved top. The design Tanguy and the team come up with is incredible, but there's a huge problem.
They've got a beautiful design, something that makes a skyscraper look like a work of art, but they can't build it.
Japanese building regulations won't allow them to build something the size that they need.
In Japan, there are tight restrictions on how large you can build skyscrapers to stop them from blocking sunlight and airflow. But fitting in 10,000 students means they need to exceed the restrictions in a big way.
It's almost more than 30%, which is quite a lot to achieve.
After lengthy discussions, the architects managed to persuade the government that this area of Tokyo needs more young, talented people, and they get the go-ahead. In May 2006, construction begins, and with it comes the first major challenge. Much of Tokyo is built on clay, silt, and sand, which is too soft to support an enormous building like the Cocoon.
We knew that the soil under the foundation was not strong enough to support the weight of the tall building.
The first thing they have to do is dig down to find solid ground.
We use piling so that our piles will reach deeper soil, which is stronger. Then the stronger soil can support the weight of the building so that the building doesn't sink.
Once they have created the 36 piles, they lay a huge slab across the top to bond them all together.
The concrete slab transfers the weight of the building to the soil directly.
In July 2006, they finally have a solid foundation to build the 668-foot-tall building. Now, they can start on the tower. With the small plot size, it will start narrow, allowing light down into the street, and then bulge in the middle to allow for more floor space. But the curving shape makes it complicated to build, especially in a country that's known for huge earthquakes.
Curved structures are at great risk of twisting during an earthquake. That's called torsional forces. So you've got to make sure that your beautifully designed building doesn't essentially rip itself apart. In Tokyo, the team building a curving, cocoon-shaped skyscraper needs to make it strong enough to withstand earthquakes. They decide to wrap the tower in a strong steel exoskeleton made from triangles. Known as a diagrid, this will resist any tremors.
Triangular frame is much stronger than rectangular frame because triangle is very difficult to deflect compared to the rectangle. Covering the building with triangular or diagrid frame was advantageous against the lateral force.
It's like a web of triangles all joined together, and as they push up against each other, they support one another.
The steel diagrid frame is then tied into a central concrete and steel core to make the building even stronger.
The inner frame is mainly against the gravity laws, and the external frame is mainly against the lateral forces.
In February 2008, they now have a building that is strong enough. The next challenge is creating the curtain wall from approximately 3,600 glass panels. Because the panels are big, an entire story high, it would be difficult to transport the complete panels through the congested narrow streets of Tokyo.
It was decided to assemble on site rather than transporting the completed panel from the factory.
With such a small plot already jam-packed with construction activity, the problem now is where to put them together. Ingeniously, they turn to the empty elevator shaft area. The next challenge is working out how to make the man-made glass exterior of the building look like a natural cocoon.
Nature does complex things seemingly easily, and when humans try to replicate it, then they realize just how difficult it actually is.
Their clever solution is to decorate the curtain wall with an organic pattern.
The irregular patterns within each curtain wall creates this amazing optical illusion that you're looking at a woven cocoon.
First, they add strips of aluminum mirroring the die-grid stills behind.
From outside, it looks like the same as the cross-bracing pattern.
Then, they add dotted lines to the glass, which will come together to form a randomized pattern resembling woven threads crisscrossing the building.
We have to do it with a computer to make sure as much as repetitive patterns, but create the better irregular looks to it. So that was a challenging part.
It's also challenging getting them up the building.
If there's a windy day, it's difficult to bring up the pieces. It's very dangerous for that matter.
The panels might shatter, raining glass on people below. Again, the elevator shaft comes to the rescue. They realize they can use it to crane the panels to the top, protected from the wind.
Lift shaft is wind-free, which is quite safer place.
Now, they can just lower them a short distance into place. Creating the curtain wall with its cocoon pattern. In March 2008, there is one final hurdle to overcome. Every tall building in Japan has to have a platform for helicopters in case of a fire.
The architect wanted a cocoon shape. They didn't like to have a flat surface on top. So it is a new challenge.
One for which the team has a great solution. If they can't build it on the roof of the building, then they will build it inside the top.
We designed a retractable roof. Back of the exoskeleton, there is a platform already installed. Hovering space is supported by 3 pairs of cross braces. Roof is opened and closed manually by hand control in emergency.
Creating a retracting platform that feels more James Bond than Tokyo College. After 2 years of creative construction and problem-solving engineering, in October 2008, the spectacular Cocoon Tower throws open its doors to students attending Japan's first vertical university.
The design of the cocoon is very beautiful.
I personally like the view, especially in the evening. You can see the evening skyline.
I like this Cocoon Tower's looks because this tower is looks fashionable and so iconic.
It's as much art as it is architecture, adding something truly unique to the built-up Tokyo skyline. An extraordinary cocoon shape that is worthy of all the challenges the team faced.
Projects that are this elaborate, this complicated, are rare. That's what makes them exciting.
See